Hi all, welcome back to SystemVerilog sessions. In this video, I'm going to discuss about clocking blocks in SystemVerilog. So what is clocking block? To specify the synchronization scheme and timing requirements for a test bench, a clocking block is used. Synchronization scheme and timing requirements for a test bench. So whatever the signals we have in the test bench, at what time we have to drive it, at what time we have to sample it, that can be controlled by using the clocking block. So to specify the synchronization scheme and timing requirements for the test bench, a clocking block is used. And depending on the environment, a test bench can contain one or more clocking blocks, each containing its own clock plus an arbitrary number of signals. So in the test bench we can include one or more clocking blocks, and each clocking block has its own clock. And also we can include arbitrary number of signals. Any number of signals we can include in the clocking blocks. And multiple clocking blocks cannot be nested. They cannot be declared inside functions, tasks or packages, or outside all declaration in a compilation unit. That means inside the clocking block we cannot declare another clocking block. Okay, it should not be nested. And we cannot include the clocking blocks inside function, task or packages, or outside all declaration in the compilation unit. The clocking blocks can be declared in the program, module or interface, but we can include the clocking blocks in program, module or interface. In these three we can include the clocking blocks. A clocking block has static lifetime and scope local to its enclosing module, interface or program. A clocking block has static lifetime. Static lifetime means the clocking block will be there throughout the simulation, and scope is local to its enclosing module, interface or program. So the scope is local to the enclosing module, interface or program. Within the module or within the interface, it has a scope. A clocking block is defined between the keywords clocking and end clocking. So whatever the signals or timing requirements we will write, it should be inside the keyword clocking and end clocking. The clocking block separates the timing and synchronization details from the structural, functional and procedural elements of a test bench. So how the clocking block separates the timing and synchronization details from these structural, functional and procedural elements of a test bench. So suppose if we don't have a clocking block and if we want to write the timing requirements for a test bench, how we will write? We have to take one procedural, we have to write the procedural code, right? We have to take one procedural blocks like always or initial block we have to write, and we have to include the delays or at what time it has to drive, what time it has to sample. Everything we have to write inside the always block in the procedural block. But when we have a clocking block, we don't have to take the always block or any procedural elements of a test bench. Just in a single clocking block everything we can include. That's why the clocking block separates the timing and synchronization details from the structural, functional and procedural elements of a test bench. Thus the timing for a sampling and driving clocking block signals is implicit and it's relative to the clocking block's clock. So clocking block's clock, whatever the timing requirements are there, that is related to the clocking block's clock. So what clock we will use in the clocking block, for that only everything is related. Okay. And signal directions in the clocking block within the test bench are with respect to the test bench and not the design under test. In the mod ports, in the last video we have seen the mod ports, right? In the mod ports we will give the direction for the signal, so that direction is with respect to the DUT, right? But in the clocking block, this whatever the signals we will write the directions, input or output or in out, that direction is with respect to the test bench, not with respect to the DUT. So this is one thing you have to remember. Now we will see clocking block declaration. So this is how we have to write the clocking block. All the timing requirements should be enclosed within clocking and clocking keyword. And CB is the clocking block name and at passage clock is the clocking event. There are some terms for clocking blocks, and when we are explaining the clocking block we have to use that terms. Okay, so this is called as a clocking event. Clocking event means the timing used to drive and sample all other signals specified in a given clocking block is governed by its clocking event. So here whatever the timing requirements are there, those timing requirements are related to this clocking event. Okay, so those times are controlled by this clocking event, and so this is called as a clocking event. And default input #1, output #2. So what is this #1 and #2? This #1 or #2 is called as a clocking skew. The clocking skew determines how many time units away from the clock event a signal is to be sampled or driven. That means here input and output is there. Input means always be sampled and output means always be driven. So for the input signal we have a #1, right? That means at one time unit before the clocking event, one time unit before the passage clock, our input signal has to sample, and output #2 means 2 units after the passage clock our signal has to be driven. Okay, this is what it means. And here default keyword tells that all the signals we declare inside the clocking block should follow this input and output timing requirements. Okay, all the signals should be sampled 1 unit before the clocking event, and all the signals declared as output will be driven 2 units after the passage clock. So why I am telling before and after, I will tell you. Okay, I will show the pictorial representation. Okay, and here you can see input and output. I have declared the signal as input and output. For input, what I have written from DUT, and output I have written as to DUT. These signals are called as the clocking signal. And why I have written like this, because while explaining I told you, so all the signals we declare inside the clocking blocks are with respect to the test bench, not with respect to the DUT. So for test bench, what is the input? From DUT, whatever the signal are coming, that is input to the test bench, right? That's why I have written it as from DUT. And what are the outputs of test bench? To DUT, what are all the inputs? Those signals are output for test bench, right? That's why output to DUT. Just for understanding purpose, I have written like this. This is nothing but all the clocking signals are with respect to the test bench, not with respect to the DUT. Okay, and only the direction I'm telling. So, and the timing requirements are also related to the test bench signals. So this is how we have to write the clocking block. And now we will see the skew, input and output skew. Here this is called as the input skew and this is called as the output skew. So what is this skew? This is the clocking event. Here passage clock I have taken, right? So this is the passage clock. This is called as a clocking event. So clocking skew determines how many time units away from the clock event. So here this is the passage clock. Input skew means before the clock event and output skew means after the clock event. Here we have a default input #1, output #2. Input #1 means signal has to sample 1 unit before the clock event, before the passage clock, and #2 means 2 units after the clock event. So this is the clock event, right? Passage clock. After the passage clock, the 2 units after the passage clock, our signal has to drive. Okay, this is nothing but input skew and output skew. Signal sampled here, signal driven here. So the point is this clock event, passage clock. Here you can take passage, neck gauge, or simple clock, whatever you can take. That is called as a clocking event. And skews are related. Skews determines how many time units away from the clock event. Okay, so this is all about clocking block declaration. Now we will see the syntax for clocking blocks. There are many ways to write the clocking blocks. We will see one by one. Okay. So first one is clocking CB at neck gauge clock. Here I have taken the clocking event with the negative edge. Okay. This is the clocking event neck edge clock, and default input #2, output #3. That means all the signals declared as input are sampled 2 units before the neck gauge clock, and all the signals declared as output are driven after 3 units of the neck gauge clock. Okay, so these are all the skews and clocking event. These are all the clocking signals. Second one is, here I have taken just a clocking event without edge. Okay, just I'm taking clock without edge, and default input #2, output neck gauge. Here you can see I'm not taking any skew number, right? Skew we can take the edge also here. So here 2 units before the clock our signal will be sampled, and at the neck gauge clock, here I have taken the clock, right? In the clock, neck gauge clock will be there. So that neck gauge clock outputs are driven on neck gauge clock. Okay, and input output. And clocking CB at passage clock. Here I have taken the passage clock. My clocking event is passage clock. Default input #1, output neck gauge. That means our signal will be sampled 1 unit before the passage clock, and output will be driven at the neck gauge of the clock. So passage means after passage, the right after the passage we will get the next negative edge, right? Neck gauge. At that time our signal will be driven. Okay, so this is what it means. And clocking CB at passage clock. Here also passage clock is the clocking event. Here default input #1 PS, output #4. So explicit declaration of time unit. Here in the previous example I have not mentioned any time unit, but here I am using PS, picosecond, right? So you can write like this also, input #1 PS, output just 4. So if you don't declare the time unit, it will take the current time unit. So where you are using the clocking block, at that block's time unit it will take, whether it is nanosecond. If your code is using nanosecond, then it will take the 4 nanosecond. So if you specifically mention as PS, then it will take 1 picosecond. Okay, so here you can mention or you don't have to mention. And next one is clocking CB at passage clock. Default input #1 PS, output #4, and input #2 PS signal name, input #3 output #4 signal name. So here you can see, here I have used a default statement also. Default means all the signals we declare inside the clocking block will follow this input and output skews. But here you can provide the separate skew for input and output signals. Okay, here even though if I use default statement, I have again declared the input skew for the signal name. Right, here you can mention the signal name, and that signal will be sampled 2 units before the passage clock, and here the signal name is there, right? So this signal also can be sampled at 3 units before the passage clock and 4 units after the passage clock. So that means here only for particular signals we can provide the input and output skews, and if you don't provide the input and output skew separately, then it will follow the default one. Okay, default input #1 PS, output #4. So if you want to separately sample or drive the signal, then you can provide like this. So this is all about syntax. Now we will see some important points to remember in input and output skews. So the first one is, if an input skew is specified, then the signal is sampled at skew time units before the clock event. So this thing we have already discussed in the last slide. Input skew means what? That time unit before the clock event our signal will be sampled. If an input skew is specified, then the signal is sampled at the skew time units before the clock event. So this is called as a input skew. And similarly, output or in-out signals are driven skew simulation time units after the corresponding clock event. So input means before the clock event, output means after the clock event. Input will be sampled, output will be driven. Okay, before and after, this thing you have to remember. Input will be sampled before the skew time units, and output will be driven after the skew time units from the clock event, from the passage or negate clock. And a skew shall be constant expression and can be specified as a parameter. So this skew is nothing but time units, right? To #2, #3, #negate. So this skew shall be constant expression and can be specified as a parameter. And if the skew does not specify a time unit, the current time unit is used. So if you don't provide as #1 PS, #1 whatever the time unit, it will take the current time unit. And if a number is used, the skew is interpreted using the timescale of the current scope. So if you are using the skew as #1 or #2 instead of negate or passage, then that skew is interpreted using the timescale of the current scope. It will take the current scope's time unit. If your current scope time unit is nanosecond, then it will take the nanosecond, #1 nanosecond, #2 nanosecond, like that. Okay, if you don't provide the time unit, then an input skew of one step indicates that the signal is to be sampled at the end of the previous time step. In other words, the value sampled is always the signal's last value immediately before the corresponding clock edge. Suppose you have a clocking event as passage. Okay, you are having a passage clock unit. So this is your clocking event, and input skew means what? The signal will be sampled before the clock event, before the passage clock your signal will be sampled, right? For example, #1 means #1 time unit before the passage clock. But when you are taking one step, input skew as one step, that means before changing, like end of the previous time step. So before changing the value, like for example 0 to 1 transition will happen, right? Passage means, so before changing from 0 to 1 the signal will be sampled. You can't tell at where exactly the signal will be sampled, but #1 step means end of the previous time step. Okay, so exactly here only the signal will be sampled. It's not like before the 1 unit before or 2 units before. The signal will be sampled at one step. So #1 step means it's like end of the previous time step. In other words, the value sample is always the signal's last value immediately before corresponding the clock edge. So before starting the transition from 0 to 1, the signal will be sampled. Okay, so end of the previous time step. So this is what #1 step means. Then inputs with explicit #0 skew shall be sampled at the same time as their corresponding clocking event, but to avoid races, they are sampled in the observed region. So if you are providing the #0 skew for the inputs, especially for inputs, if you are providing the skew as #0, then the signal will be sampled in the clocking event. For example, if you are taking passage clock, then your signal will be sampled in the passage clock only. but to avoid races they are sampled in the observed region. Okay, just for avoiding the race it will be sampled in the observed region. So I have already made video on event regions. If you want to see, you can go and watch. Okay, in the observed region the input will be sampled. Similarly, if you provide the hash 0 skew for outputs, so if you provide the explicit hash 0 skew for the outputs, then signal will be driven at the same time as specified clocking event. Here also, if you are having the passage clock, then your signal will be driven at passage clock only when you provide the hash 0 skew for outputs. But to avoid the race, it will be driven in re-NBA region. Okay, in the re-NBA region. So this is one thing. For inputs it will be sampled in the observed region. For outputs it will be driven in re-NBA region. And skews are declarative constructs, thus they are semantically very different from the syntactically similar procedural delay statement. So this skews is also delay, right? But these delays are different from the procedural delay, like what we will provide. There are many ways to write the delays, hash hash 1 or hash hash 2, but skews are different from the syntactically similar procedural delay statement. So this thing you have to remember. And any signal in a clocking block can be associated with an arbitrary hierarchical expression. So we can provide our clocking signal as a hierarchical expression. So our signal can be associated with hierarchical expression. Here you can see clocking CD1 at passage clock, input hash 1 step state equals to top dot CPU1 dot state. Right here, this is called as a hierarchical expression. So our signal in the clocking block can be associated with an arbitrary hierarchical expression. And the below one is like here also we can provide like this: clocking mem at clock, input instruction opcode reg A reg B 3 down to 1. So here also like this also we can provide for clocking signals. Okay, so this is about input and output skews. Now we will see default clocking. So what is this default clocking? One clocking block can be specified as the default for all the cycle delay operations within a given module, interface, program or checker. So we can make the one clocking block as default clocking for all the cycle delay operations. So that is called as a default clocking, and we will use the keyword as default clocking only. Okay, default clocking is the keyword used to make the clocking block as default clocking. Only one default clocking can be specified in a module, interface, program or checker. Only one clocking block we can make it as a default, and a default clocking is valid only within the scope containing the default clocking specification statement. That means where you are writing the default clocking statement, in that scope only the default clocking will be valid. And this scope includes the module, interface, program or checker that contains the declaration as well as any nested modules, interfaces or checkers. So this scope is nothing but your module, interface, program or checker, and that module or interface or program can contain the declaration as well as any nested modules. So your module can have another nested module inside it. Okay, so this is possible, and it does not include instantiated modules, interfaces or checkers. So your scope, your module should not contain the instantiated modules, but it can have a nested modules. Nested modules means what? Inside the module you can write the another module, but your module should not include the instantiated modules, interfaces or checkers. So this is about the default clocking, and you have to remember these points when you are using the default clocking block. Now we will see how to declare the clocking as the default. So here I have a program. I am passing the clock and data here, and if you see here, default clocking bus at passage clock, in out data and clocking. So if you remember in the last example, when I am writing the clocking block, we have used the default keyword inside the clocking block, right? That means our signal, whatever the signals we declared inside the clocking block, input or output signals, input signals will be sampled at the specified input skew, and output signals will be driven at the specified output skews. So their default we have included, means all the signal will follow that input and output skews. But when we use the default keyword with the clocking block itself, then that clocking block is called as a default clocking. That means when you have multiple clocking blocks with the different clocks, then the specified clocking block as a default will be your default clocking block. Okay, here I have used default statement with the clocking block. So this bus is a default clocking block. Now when you have more than one clocking block with different clocks, here I have used clock. If you use the another clocking block as clock 1 or clock 2, then the clocking block which is specified with the keyword default is your default clocking block. Okay, so this is called as a default clocking. This is how we have to write. You have to use the keyword with the clocking block itself. Okay, and this is some logic inside it. Initial begin hash hash 5, and if bus dot data is equals to 10, then perform some operation. So this is how to declare the clocking block as a default clocking block. This thing you have to remember. And assigning an existing clocking to be the default, that means here I have a module processor. So inside the module I have a two clocking blocks, clocking bus A and clocking bus B. So here bus A is with respect to the clock 1 and bus B is with respect to the clock 2. Here I have two clocking blocks, and this processor module has another module CPU. That means this module is called as a nested module. Okay, inside the module, if you specify another module, then it is a nested module. So here I have a nested module. Inside the nested module, I'm making the bus A as a default clocking bus A, and this default clocking is valid in this scope only. Okay, so the wherever you have written it as default clocking, there only it is valid. And default clocking bus A, I'm making the bus A clocking block as a default. That means whatever the signals we have in this module or test bench, all the signals will be following this timing requirement specified in the bus A, because it is a default. So even though if you have two clocking blocks, it will follow the timing requirement specified in the bus A. That is nothing but default clocking, right? So here I have a default clocking of bus A, and here some logic is there. This is how to assign an existing clocking to be the default. Now we will see synchronous events. So what is the synchronous events? Synchronous event in clocking block means now we have a clocking block with clock event, input and output skews and clocking signals. So if you want to wait for the clock, then how to wait for that clock? That is by using the event. Okay, explicit synchronization is done via the event control operator at, which allows a process to wait for a particular signal value change or a clocking event. So by using this at operator, we can wait for the clock in the clocking block. Okay, we will see the examples. So here at rambus.ack1 means here I am waiting for the ack1 signal which is inside the rambus clocking block. So how I am accessing the clocking block signal? By using the dot operator. Rambus is the clocking block name. I am waiting for the ack1 signal which is declared inside the clocking block. Wait for the next change of signal ack1 of clocking block rambus. So this is how we have to wait for the signal at rambus.ack1. Okay, and if you want to wait for the clock, then you have to use the clock inside the clocking block by using like this only, at rambus.ack1. ack1 can be your clock also. Okay, that means you are waiting for that clock. So here I am waiting for the signal ack1 which is declared inside the rambus clocking block. And this is at rambus. Here I am waiting for the clocking block. I am just using the clocking block means wait for the next clocking event in a clocking block rambus. So in the rambus, whatever the clocking event I have taken, for example passage clock or negate clock clocking event, I am waiting for that clocking event. So in order to waiting for the clocking event, we have to use the clocking block name. Okay, at rambus. So here I am taking rambus. In the previous syntax I have used CB, right? So at CB you can use, or at rambus. And here at passage rambus dot enable, this means I'm waiting for the passage of enable signal. So enable signal is declared inside the rambus. That's why I'm using rambus dot enable. In order to access the signals declared inside the clocking block, we have to use the dot. So I'm waiting for the positive edge of the signal enable which is declared inside the rambus clocking block. Then at negate dom dot signal. So here I have a signal which is inside the dom. Okay, so I'm waiting for the negative edge of that. Wait for the falling edge of the specified 1-bit slice dom dot signal A. And here the index is evaluated at the runtime. So here this is array, right? So this will be evaluated at the runtime. And at passage dom.sig1 or dom.sig2. Here I'm using two signals by using the OR operator. OR means if any one of the signal can happen first. So based on that change will happen. Okay, wait for either the next positive edge of the dom.sig1 or the next change of dom.sig2. Waiting for the both. So whichever happens first, then it will take that. Okay, and wait for either the negative edge of the sig1 or positive edge of the signal. So here also I'm using OR operator, waiting for either of the signal. So whichever happens first, according to that changes will happen. And wait for the edge. Here you can see at edge dom.sig1. So I'm using the keyword edge here. Edge means it can take positive edge also, negative edge also. So this is equivalent to at negedge dom.sig1 or posage dom.sig1. Okay, I'm waiting for the negative edge of the signal 1 or positive edge of the signal 1. Whichever happens first, according to that changes will happen. Okay, so these are all the ways to wait for the clocking block signals. Okay, synchronous event means you can wait for the clocking event or clocking block signals by using the at operator, and you have to use the clocking block name to access the signals. Okay, clocking block name dot signal name. So this is about the synchronous events. So if you have any doubts, you can ask in the comment section. Okay, thank you.